back. I have a question.
Okay. Yes, go ahead.
Okay, so I'm pretty sure I follow to why you start at 53.1 degrees,
Uh-huh.
but a set of a set of vectors, and it wasn't labeled like ABC. How would we know which one to go with?
You can start with any of them because that's one of the rules. It turns out, if you think about displacement, like walking from your house, if you change the order of the trips that you make, like one of them's due east for 30 meters, and the next one is at 45 degrees north of east for 20 meters. If you did the 20 meters first and then the 40 meters second, it'd still come out the same. So you can actually start off with any vector you want. I just did ABCD because that's the order that I drew them in. But yeah, it turns out that A plus B is equal to B plus A, and A plus B plus C is equal to A plus B plus C.
Okay, thank you.
So like all those rules that you know from algebra. And in fact, this is called vector algebra. I will tell you the reason. In fact, there's a larger idea called an algebra. Notice how I said that, an algebra. So you can make up things that form an algebra. And those things that form an algebra are basically any things that follow those rules that you guys learned when you're first doing pre-algebra. A plus B is got to equal B plus A. Also, the negative or the additive inverse is the negative of the number, or the multiplicative inverse is the reciprocal of a number. So some of those rules are what's required for something to be an algebra. And it turns out one of those algebras is a vector. Vector algebra is a vector.
Okay, thank you.
So yeah, it's kind of bummed out that I've left off all that stuff. The good news is I already have the video online of another vector addition problem, but we're doing this one now so we can see. I've drawn the first vector, 53.1. I've drawn it in black just so I didn't have to label it. I've drawn the second vector in blue and underlined it blue. Notice it should be twice as long as the other one. I also noticed that this thing automatically started drawing these vectors like I like them, like it's made a straight line. So evidently there's a new thing I can learn. I just haven't figured it out yet. Now vector C is going to be 141, which is almost 3 times as big as vector A. It's going to be 141.4 meters, and it's going to have a compass heading of 225. Well, I know 0 is up, 90 is in the positive x direction, 180 is in the positive, or excuse me, in the negative y direction. And then if I add 45 to that, I get 225. So I know the next vector is in fact going to be in the third quadrant. And I will draw again a little imaginary coordinate system at the head of that vector. That's the key thing to do. I now know that I'm going to have to make it about 3 times as long as this vector. And it's going to have to split the uprights here. That looks pretty good to me. And this angle right here is 45 degrees. Okay. And that one really should have been a different color, but what I'll do is I'll mark this as that too. Okay. Now at the head of that vector, I need to put the vector D, which is supposed to be 200 meters, which really should be 4 times as big as A. And it's supposed to be at negative 30. So negative 30, I go from the positive x-axis and go down 30 degrees. So in this case, I'm going to make this black. Nope, I haven't done red yet. I'm going to scratch that. I'm going to make it red. Okay, and I'm going to do negative 30. Whoa, I didn't learned from that last time. So this angle is 30 degrees. And now I should be able to take this vector and just move it, but no, I can't. Okay, so there's probably some way that that vector can be moved. Let me try this real quick. Keep them going back a little bit. Yeah, get up there. Yeah, that's good. Okay, so now I'll try this vector again. Okay, so there's my vector D. Now, the main reason I did all this stuff is I need to have some idea where it's going to be. Now, I didn't really do anything. You should be, I mean, if you were doing this with paper, you'd actually would like say, make up some scale where like 50 meters is equal to, let's say, is equal to this distance on paper. So when you're actually on paper, this distance, which notice I tried to draw about the same as the length of the black vector, that distance is going to represent 50 meters in reality. Let's say on paper. So that's really like a scale for you. And you could actually measure it relative to these little blocks or measure it in centimeters or something like that. And then you say 1 centimeter on paper is equal to 50 meters in real life. And you can use that as a conversion factor because ultimately what this means is the resultant vector, which is going to be, let's say it's going to be this green color right here. Well, that didn't change color at all, did it? Let's undo that. Let's do that. So the vector that's drawn from the origin to the head of the last, that is the resultant. So that really is what I'm predicting the resultant to be, which isn't a good vector. It's going to be short and all that stuff. But anyways, I didn't draw that very well to scale, but that's what your resultant is. So when you drew this, you could then measure the length of that little green vector, and then you use the scale to convert it to a non-paper unit, because you've got a certain number of centimeters. You could divide it by the number of centimeters on the paper that equals 50 meters, and then multiply that by 50 meters, and that'll give you the actual dimensions in reality. And then you also use a protractor to measure downward, say, from the positive x-axis, and that would be your negative of your angle. Okay, so in other words, you put a negative in front of that number that your protractor gave you, and that would be it. What we're going to do is we're going to realize that vector A has an x component and a y component, and I'm going to take the time to treat positive components as if they're green and negative components as if they're, let's say, red. Okay, so I can see right now that looking at this vector right here, okay, I can see that it has a positive, oh no, let's undo that. Okay, it has a positive x component, which is right there, and it has a positive y component right there. And I also see that sine of 53.1 is equal to opposite, which would be a sub y, over hypotenuse, which would be a, and cosine of 53.1 would be adjacent, which is a sub x, over the hypotenuse, which is a. Okay. Similarly, I can move this down here a little bit, and I see that this has a positive, vector B has a positive y component, and it has a negative x component. Okay. Plus, I can see that the sine of 30 degrees is equal to opposite, which is b sub x, over hypotenuse, which is just b, and cosine 30 degrees is just equal to adjacent over hypotenuse, so that should be b sub y over b. Now I can look over here. This one has, in fact, a negative x component and a negative y component. And I can see, for instance, that sine of 45 degrees is equal to opposite, which is c sub y over hypotenuse, which is c, and cosine 45 degrees is equal to adjacent, which is c sub x over c. And then finally, the last vector d, it's going to have a negative y component like this, but it will have a positive x component. I think we did green for that, right? Yeah. Right there. And in fact, this angle is 30 degrees. So this angle must be 60 degrees. So I could say sine of 60 degrees is opposite, which is your x component. So that's going to be d sub x over hypotenuse, which is d. And cosine 60 degrees is going to be adjacent, which is d sub y over d. Okay, so I really want you guys to take the time, until you've done this maybe 100 times, I want you to take the time to write out each of the trig functions as as you're forming the components. In other words, take the time to write sine equals blank over blank and cosine equals blank over blank, and then that'll keep you from making careless mistakes. And by noticing the signs, you're going to actually force them. So the way I'm teaching you here is such that you never, ever will put a negative angle into a trig function. Okay. So I'm going to write now, I'm going to say AX, which we discovered was a positive. So I force a positive there. Clearly AX is going to have to be A times cosine of theta, but that's 50.0 meters cosine 53.1 degrees. But you remember cosine of 53.1, if you see that, that's 3/5, right? Cosine of 53.1 is 3/5. So 3/5 times 50 is going to give me 30.0 meters positive. AY is going to be 50.0 meters times the sine of 53.1. If you looked at that special angle over there, again, this is positive 2, but if you looked at that special triangle again, you'd see that's 4/5. So this is going to be 40.0 meters. I'm going to try to write a little smaller so I can fit this in. BX, we decided, was a negative, so I'm going to force that negative there. It's going to be 100.0 meters times what we found was BX was found by using the sine of 30 degrees. The sine of 30, if you look, should be 1/2. But you look over here, sine of 30 is 1/2. So that's 1/2. So that's going to be negative 50.0 meters. And B sub Y is going to be, that one's going to be actually positive. So that's going to be 100.0. I'll leave the units off so I can have a little bit more room, times the cosine of 30 That's going to give us, if you look at cosine of 30, you can see cosine of 30 is 1.73 over 2, or a square root of 3 over 2. So basically, I'm going to divide this by 2, which would make it 50, and then multiply it by 1.73. So really what I'm doing is multiplying 1.73 times 100 and then dividing by 2. So 1.73 times 100 is going to give you 173. If I divide that by 2, that'll be 50, 85, 86.5. So I'm going to say this is positive 86.5 meters. I'm trying to do that without a calculator, but I'll double check just for this one, just to keep from having any problems. First off, I said the square root of 3 is about 1.73. It's 1.732 to be honest with you. Then if I divide that by 2, then I get 0.866. So I call it 865 because I was rounding to that. So that's fine. That's close enough. Okay. Now I'm going to do C sub x. And we see that C sub x had a negative x and a negative y components. So I'm going to say negative 141.4. And according to this, C sub x is given by the cosine 45, which is, of course, 1 over the square root of 2. I think y'all can recognize this 141.4 as 100 times the square root of 2. So if I take 100 times the square root of 2 and divide it by the square root of 2, I'm ultimately just going to get negative 100.0 meters. Similarly, C sub y is going to be a negative 141.4 sine 45. That's going to also give me negative 100.0 meters. And we're almost done. D sub x, that one's going to be 200 meters. Notice D sub x is a D sub x has a positive x component but a negative y component, so I'll put a plus there. So 200.0 times what we found was D sub x is found by multiplying d by sine of 60. So times the sine of 60. We knew the sine of 30 was 1/2, so the sine of 60 must in fact be root 3 over 2. So if I divide that by 2, I get 100, and then times root 3, that should be 173. So I'm going to say this is positive 173. Double checking, of course, you can see that the sine of 60 is in fact root 3 over 2. And that's meters. And then D sub y is going to be a negative. So it's negative 200 times cosine 60 degrees. Cosine 60 is 1/2. So that's negative 100.0 meters. Now, when I'm teaching this for like algebra-based physics, I'd make a whole table. I make a table where you have the name of the vector as one column, so A, B, C, and D. Then the next column is the magnitude, and the next column is the angle, but I force them to automatically convert it to that counterclockwise rotation from the positive x-axis. And then they can just blindly use a formula where, you know, the magnitude times the cosine always gives you x, and the magnitude times the sine always gives you y. But you guys are smarter than that, so you can and are more I shouldn't say smarter than that, I'm sure you are, but that you guys are more proficient with this. So I think you're cool enough to use just the angle from the vector to the nearest axis, and that's what I'm really doing here. And I force myself to do the signs. This is really what you should do. There are many ways you can use your calculator to do vector addition for you. I want you to never use that. Wait till you finish your degree, then use that, okay? Or maybe use it as a check every time you do one. Just do it really quickly and see if you get the right answer. So now I'm going to add up all these, and that will give me R sub x, and I add up all these, and that'll give me R sub y. Remember, R being the resultant. So I got 30 minus 50 is negative 20, negative 120. So this is positive 53.0 meters. In this case, I got 40 plus 86.5, that's 126.5, minus 100, that's 26.5, minus 100 again, that would be essentially 27, so we'll call that 33, so that would be 73.5. Whoa. Negative. Okay. Anybody wants to check my math on that? I'll need to try it real quick just to make sure. 40 plus 86.5 minus 100 gives me 73.5 negative, and 30 minus 50 minus 100 plus 173 gives me 53.0. So both of those are good. So now what I do, there's a lot of ways you can write vectors. For instance, we could go ahead immediately and just say R is equal to 53.0 meters I hat minus 73. Actually, I'd say plus, and then I put a parenthesis here, and I'd say minus 73.5 meters J hat. That would be acceptable, but only if I asked you to give it to me in IJK notation. If I asked you to give, if I didn't ask you at all what notation to give it to you in, to me in, then you're supposed to assume that it comes back in the same way that was given to you. So all these are in magnitude and direction format. So that's what you should expect. So how do we do that? Well, the first thing I'm going to do is I'm going to draw an XY coordinate system so that when I show this to my teacher, say, I will have a description of exactly what I mean by theta and by R. So the magnitude of this R vector, we're going to have to get, and the direction of this R vector we're going to have to get. So I'm going to draw the X component, which should be about 53 meters. And that's in the positive X direction. And now I'm going to draw the Y component, and that's going to be in the negative Y direction, and it's going to be a little bit bigger. That's going to be 73.5 meters. And then I'm going to complete the parallelogram because they're tail to tail. And I'm going to say the actual vector is this guy. And this right here is the angle theta. So I know R is equal to the square root of 73.5 squared plus 53.0 squared. Now, technically a meter's in there. So when you square a meter, you get meter squared. And then you add a meter squared to a meter squared, you still get meter squared. And then you take the square root of meter squared and you just get plain meters. So in this case, I'm going to do 73.5. Actually, I'm going to do square root 73.5 squared plus 53 squared, and that gives me 90.6 meters. Okay, so that's my magnitude. That obviously is way off from the drawing. You can see how short the vector was in my drawing up at the top. It appears to be shorter even than A, but again, I didn't do any real measurements. I was just estimating everything. So that's to be expected. Now I also say theta is the inverse tangent of the Y component, which would be 73.5 over the X component, which would be 53.0. So I'm going to do tangent inverse. Notice I'm not using any signs. 73.5 divided by 53, and this gives me 54.2. degrees. So another way of writing R is equal to 90.6 meters at, since I have this drawing, I can just say at theta equals 90.6, or I can go ahead and say negative 90.6, or darn it, wrong thing, hold on. Negative 54.2 degrees. Because it's measured clockwise from the positive x-axis, that makes it a negative angle. So either one of those is acceptable. So there's how you add a vector, or four vectors. Go ahead.
Just to clarify, when we're doing this on the test and stuff, it's okay to leave a negative angle. We don't have to make it a positive angle.
Luckily, I've made all my tests into multiple choice.
Okay.
So you'll have just something to match, so it makes it a little easier. But yeah,
Okay.
I would accept a negative angle if I was doing a free writing test.
Okay.
In fact, if you have that last drawing, you can do anything you want. You can just say, you can write R equals this and theta equals that and circle it, and that's it. Because I can see from your diagram exactly what you mean.
Sounds good. And then when we're actually drawing the diagram, how important is it for it to be as accurate as possible?
On the test, none. But if I was asking you to do a problem graphically, then you know, that's a whole nother problem in itself. Then yeah, it should be super, super accurate. Get as tight as you can. Make sure you make the things, you know, use a protractor that's measured at least in half a degree segments, and measure really to 2 decimal places and all that good stuff. But yeah, the drawings, that one I did is more than good enough.
All right, thank you. I was just wondering because I need to get a protractor.
Yep, no problem. Anybody else have any questions on that?
You said the angle can be negative.
Yes, the angle can be negative, but when you say it's negative, that means to me that it's measured clockwise downward from the positive x-axis.
Okay, thank you.
Okay, that's just a typical mathematical notation for it. All right, I wanted to give you guys a break, but I ran too long, and now I've discovered I have not recorded this, so I am going to. I'm still going to post this tonight, but I'll do something else for those first problems and make up a new video for that. And I'll put that up later as well, but you'll have this one in its entirety. And the fact that I flip back and forth between that page and this page helped you a little bit. Remember what we went over basically is first thing we did was I solved that problem of a car accelerating from rest with an acceleration of 2.0 meters per second every second, and going across an intersection that is 30 meters wide, 30.0 meters wide. And I asked how long it would take. Then I asked how fast it'd be going when it got there. So that's me solving that. I then did something to teach you that a negative acceleration does not necessarily mean something slowing down. So in the first case, I did 2 different coordinate systems for a car speeding up from 0 to positive, or from 0 to 20 meters per second in 4 seconds. And then I did a car actually slowing down from 20 meters per second to 0 meters per second in 4 seconds with 2 different coordinate systems. And you see, again, you can get a negative or a positive in both of those cases. So I might not even have to make something like this, but I'm probably still going to. But just covering this, I think y'all can get enough. Finally, I started into chapter 3, and I said a vector is anything with magnitude and direction. And I said a typical example of a vector could be an acceleration vector, or excuse me, can be a force vector, or in this case, we were just talking about directed line segments. So these arrows can represent a vector. And since the vector has magnitude and direction, at least in kindergarten way of us dealing with vectors, that means you can move it around anywhere you want as long as you don't stretch it or compress it or twist it. So you don't change its magnitude or direction. You can move it anywhere you want. That's going to come in handy. I told you if you multiply a vector by a number bigger than 2, that makes it longer by that factor. If you multiply it by a number small, or excuse me, yes, it's bigger than 2. if I multiply a vector by a number bigger than 1, then basically the magnitude becomes the magnitude that it originally had times that number, but the direction doesn't change at all. If I multiply it by a vector that's smaller than 1, then I shrink it, and I shrink it by exactly that factor. So if I multiply it by 1/2, then if the vector was originally 10 meters long, now it's going to be 5 meters long, but the direction will be the same. The time that you change the direction is when you actually multiply by a negative, and in that case, you flip it around 180 degrees, but everything else is how that's worked out. I then showed you how to add a vector. And the typical example was one straight part of your trip would be a displacement vector, and the second straight part of your trip would be a second displacement vector. At the end of those two parts of displacements, the new displacement is the sum of those two displacements. So I showed you that if you put vectors head to tail, then you just draw a vector from the tail of the first one to the head of the last, and that's the sum. When you have vectors that are tail to tail, though, you have to complete the parallelogram and then draw from the common tail to the diagonally opposite corner, and that's the sum. If you want to subtract vectors, we had to use that definition of subtraction from algebra. A minus b is defined to be a plus the opposite of b, which means the negative of b. So when you write two vectors that are head to tail, like I did here, d1 and d2 in red, first thing I want to do if I want to calculate d1 minus d2 is I multiply d2 by a -1, and that means I just basically turned it into that blue vector where the head of the vector is now down at the tail of the original d2. And then what I did was I slid it along d1, and by doing that, now I have it in head to tail format, and I just draw from the tail of the first, which is the top left corner, to the head of the last, which is the bottom right corner, and you can see that I in fact got d1 minus d2 is this guy. When I had d1 and d2 in tail to tail and subtracted them, that became the easiest scenario, because d1 and d2 are tail to tail. All I had to do was flip d2 by putting the head on the opposite end, and when I did that, they were automatically in head to tail formation. So I just drew it from the tail, which is the top left, to the head, which is the bottom right, and that gave me, in fact, the how you draw vectors to subtract them. I told you that the resultant vector R is another name for the sum of any number of vectors, and I told you that the equilibriant is a vector that would cancel out that vector by being its negative. Then I showed you this coordinate system, which has the y-axis corresponding to the north direction, which is a compass heading of 0 degrees. The x-axis is pointing east and has a compass heading of 90. The negative y direction is pointing south and has a compass heading of 180. And the negative x direction is pointing west and has a compass heading of 270. And then I talked about these special triangles so that I could do the vector addition problem without any calculator. Okay. And then, of course, I did that. So you can see the critical part was really breaking these individual vectors down into components and choosing whether they're positive or negative components. And to do that, I really want you to think about, like when I did vector A, see the little black vector right there? I have to go from the tail of that little black vector to the head. I can go along the x-axis first, or I can go along the y-axis first. It doesn't matter. But the next one's got to be the other axis. So if I go along the x-axis, I have to go to the right, and then I have to go up parallel to the y-axis. So the right is a positive direction and up is a positive direction. That's how I knew that was positive. However, if you look at B, I had to go up along the parallel to the y-axis, so that's a positive, but I had to go to the left once I got to the end of that vector to get to the head. So that's a negative x component and a positive y component. So that was the really big issue with this, was getting those component signs right. And that's the thing that generally screws students up. They want to just blindly use cosine to get the X. They want to just blindly use sine to get the Y. You can't do that unless you're going to consistently convert your angle to measured counterclockwise from the positive x-axis. And even then it's going to screw up because, for instance, the first and third quadrant has tangent being positive, even though tangent in the third quadrant is a negative x component and a negative y component. So you can see the signs can screw things up. So I just choose not to do it that way at all. And that's it. That was the whole vector rigmarole. Now our class runs from what, 5:30 to, is it 7:50? I think that's what it is.
Yeah, that's it.
Okay, cool. So I got more time than I was thinking. Would it scare me for a little bit there? Okay, so let's go ahead and take that. Let's take an 8-minute break. So let's come back at 7:15 and we'll get started. I don't have that much stuff left to do. So please help me remember to hit pause so that I can start recording when you come back. But I will see you at 7:15, and I'm here if anybody has any questions.
I have a quick question.
Yes. And start up the recording again. I'm going to try to address Brian's question as well here. So I'm going to share my screen again, which is a lot more of a pain than I have to. All right, so do this. Hey, don't do that. Learn your, hey. There it is. Kill this. Okay, so I'm going to go back. Brian evidently was asking something about those acceleration problems. So I just wanted to show, reiterate to everybody. So in this first example, I am picturing the vehicle starting at the origin at 0 miles or meters per second. And then sometime later, 4 seconds later, in fact, it's at some positive x position moving to the right, which is the positive direction, at 20 meters per second. So V final minus V initial is 20 meters per second minus 0 divided by 4. That gives me a positive 5 meters per second every second. In the second diagram for that first problem, I am still going to the right, okay, but I've drawn my positive x-axis going to the left. So I started at some negative x value with a velocity of 0, and then I ended up at some smaller negative x value with v equal negative 20.0 meters per second, because I'm going in the negative x direction. It's got to be negative 20. So the final velocity minus initial velocity is negative 20 meters per second minus 0 divided by 5. That gives me negative 5 meters per second every second. So that is, in fact, exactly what you expect. A negative acceleration can be speeding up, but it's normally speeding up in the negative direction. And the second part, we actually have something that's physically slowing down. We're going 20 meters per second, and it slows down to 0, in other words, to stop, in 4 seconds. If it's initially doing 20 meters per second to the right, and we call the right the positive x direction, then the final minus initial would be 0 minus 20 meters per second over 4. That gives me negative 5 meters per second. So in that case, the negative really did mean decelerating. But if you flip the coordinate system, then you have negative 20 is what it's going initially to the right, because the x points to the left, and then 0 at the end. Then you have 0 minus negative 20 meters per second. That gives you positive. Remember, minus negative is plus a positive. That gives you positive 5 meters per second every second. Did that help you, Brian, if you're in here? Okay, he might not be back. That's okay. Just wanted to make sure that was one of the chat questions that came up. So I did do all of this addition. The next thing I want to do, though, is we're going to work on projectiles. Okay, so this is projectile motion. So we talked about that that position vector that displacement vector, you can sort of always imagine that as pointing to you. So we can imagine, for instance, that the position of a projectile might be called by a vector called R. Again, it could have been X, it could have been D, whatever, doesn't matter. I use that. I use R generally. And we know that fundamentally the position is given by one of those kinematic equations as a function of time. So if I wanted R as a function of time, I would write 1/2 a sub x t squared plus v0 sub x t plus x0, and that would be my x component at any point in time, assuming constant acceleration is all we had. So okay, so if we assume the acceleration is constant, we know that both equations are that. This would be 1/2 a sub y t squared plus v0 sub y t plus y0, and that would be in the j hat direction. So if we just assume that all went in the xy plane, that would be a result. Now, the whole thing that makes us be able to treat projectiles this way is if you look, there's a figure in your book where a yellow ball and a red ball are basically fired or let go at the same time. So the red ball is actually dropped at the exact same instant a yellow ball is shot out horizontally from a little sort of cannon, if you will. And then it takes a series of photos, like every 10th of a second or every 100th of a second or something. It takes a photo, and you can see them side by side. And what you see is at t equals 0 seconds, the red ball and the yellow ball are at the same height. And then at t equal 100th of a second, the yellow ball is moved over a little bit because it was shot horizontally, but is still is the same height as the red ball. And then again, as the red ball is the same height, as the red ball is the same height. So what that tells you is that this y acceleration that happens as a result of g, that is unaffected by the object being shot horizontally, being shot upward, being shot downward. It's going to continue to accelerate. The only thing that changes if it's shot upward or shot downward is that V0y right here. If it's shot horizontally, that V0y is 0. If it's shot upward, it'll be a positive number. If it's shot downward, it'll be a negative number, assuming you're using upwards as the positive direction. And of course, G would be negative, or the acceleration would be negative. So if we make further assumption that there's no air resistance, so assuming no air resistance, well, that means that A is just equal to negative G in the j hat direction. Okay. And if I also assume x0 is equal to y0 is equal to 0, i.e. it starts from the origin, then I can get R as a function of t being V0. Notice it's V0x. I'm gonna go ahead and say what this is. This is going to be V0 cosine theta. So V0 cosine theta times time, all of that times I hat, plus, let's say, V0 sine theta times time minus 1/2 g t squared times j hat. That is our position vector for a projectile. So if I just make those assumptions that I did, which is there's no air resistance, therefore the acceleration is just negative g in the downward y direction, and the initial position is the origin, then this always works, this vector here. Now, are you going to work it in a vector? No, you don't have to. But it's neat to know that you can do that in principle. So it should just sort of show you that. Not only that, I can show you from this, how to take a derivative of a vector, right? Because we're learning, as this semester goes on, we'll be learning what's called vector calculus, which was invented in the 1860s by Oliver Heaviside and another guy by the name, I think his first name is Stephen Gibbs. But I might be wrong on the first name, but Gibbs, as in Gibbs free energy. Those two guys independently invented vector calculus while studying electricity and magnetism around the 1860s. So it's not that old of a mathematics. In other words, it's not like calculus. It's actually quite a bit newer. But we know, for instance, just like we did in one dimension, that the velocity as a function of time is the derivative of the position as a function of time. So the cool thing is, as long as you've got it in terms of I, J's, and K's, those vectors just slide right through derivatives. We can just treat them like a constant. There's no need to do it. If, however, you're using cylindrical coordinates, where you have a R vector that's a function of theta, which actually has an I hat and a J hat in it, you'd have to convert the R hat into IJK notation, and you have to convert theta hats if you have that in terms of IJK notation. But the Z hat would be fine, or the K hat would be fine. If you're using spherical coordinates, the same thing, that has a theta and phi dependence. So you have to, again, write that R hat vector in terms of theta, phi, I hat, J hat, and K hat. But like I said, as long as you're dealing with I and J, you don't have to derive them or take a differential of them or a derivative of them. So this is just a constant. The initial velocity's magnitude and the cosine of the initial velocity's angle, those are just constants, and it's multiplied by t. So a constant times t, its derivative is just a constant. So I get v0 cosine theta times I hat is the first derivative of the x component. Now I'll say plus, and I do the same thing with the y component. I'm going to take a derivative of all this. The j I'm going to ignore, but you see this is a constant. V0 sine theta is a constant times t. So when I take the derivative of that term, I just get V0 sine theta. And then when I take the derivative of negative 1/2 gt squared, I get, of course, negative 2 gt times 1/2. So that just becomes negative gt. And that's in the j hat direction. Okay, so now I've even got a velocity vector. And in fact, if I want an acceleration vector, I know that's dv dt. Obviously, this is a constant now, so I get nothing there. This one's a constant as well. The V0 sine theta is a constant. The V0 cosine theta is a constant. So I get 0 for those derivatives. But the negative gt just gives me negative g j hat, which is exactly what I suggested right here. Does that make sense to everyone? So, yeah, go ahead.
Could you clarify what j hat and I hat mean?
Gotcha. Okay. Yeah. So I completely forget. Some people have not had this. So what the I hat and J hat and K hat are is if you drew an XYZ coordinate system like this. So X is coming out of the board or out of the screen. Y is to the right and Z is up. So, or excuse me, Z is up. I don't know why I wrote it there. Okay, what you can do is you can define a unit vector. And when I say unit, I literally mean it's a vector whose length is 1, period. No, not 1 meter, not 1 inch, not anything, just 1. Okay, that vector in the x direction is called I hat, and the hat is what we use to indicate that it's a unit vector. Okay, it's also called in some books x hat. So you can do that if that makes it less confusing for you. A unit vector in the y direction is called j hat, and that's also can be called y hat. And then a unit vector in the z direction is called k hat, which can also be called z hat. In actuality, like in the math departments, they'll call that E1 hat, and they'll call this E2 hat, and they'll call this E3 hat. So that's another notation. I just use the IJK or the X hat, Y hat, J hat, K hat, excuse me, X hat, Y hat, Z hat, excuse me. So that's what it is. It's just when you have your vectors in coordinate notation, so that you actually have the X coordinate, the X component, the Y component, and the Z component, then you can just write those components in front of I hat or J hat or K hat, whichever one it's for, and it gives you the vector without having to ever draw a diagram or anything. So that's kind of nice. So yeah, I'm sorry I sort of jumped through that. I just sort of assumed everybody had covered it, but a lot of people might not have seen it. So thank you for asking. Another thing that can come from that is there's another way that you can write these vectors too. So you normally write a vector A as A sub X I hat plus A sub Y J hat plus A sub Z K hat. So that's sort of the beauty of this notation, is you can just write vectors really succinctly, but there's an even easier way I allow you to do, and I just write A sub X comma A sub Y comma A sub Z, like that. So that's an even shorter way of writing it if you want to. Did that help?
Thank you. Yes.
No problem. All right, so now that we got that, we can actually solve a projectile problem. I'm going to actually solve a projectile problem, and I'm not so pedantic that I'd use this vector and work it all out that way, but you could if you wanted to. I'm just not interested in doing that, but I'll refer back and forth to it. So let's imagine a projectile, a very special case of a projectile, which takes place in the X, Y plane. So there's our x-axis. And what I'm going to say is the initial velocity is a vector v0 at an angle theta. Okay. That vector will in fact follow a parabolic path, and it's going to land over here at what I call the range, which is a question mark. I don't know what it is. All I'm going to know is V0 and theta. I know V0 and theta, and X0 equals Y0 equals 0, and A is equal to negative G J hat. Okay, so that's the stuff I know. Everything else I write up here, I'm not going to know. I can say that this right here is the height H. Whoa, Nelly. Let's kill that right now. Okay. Is the height H. I can call this time at which it happens T sub 1/2. That's a question mark, and that's a question mark. I can say this time right here, T L, which I'm meaning T landing. And I can say let's take it off of that. I can say this is V final and this is phi. Okay, I don't know those either. Okay, but I've also decided by making it this way that the initial and final heights are the same. So if you don't care about the final range and the final time and the final velocity, then you can use these results for anything. But if you're wanting to use the range, the final time, and the final velocity that I derive here, then you're going to have to only use problems where the projectile is launched and lands at the same height. Okay, that's the key point here. So the first thing I might want to find is, what is h? Well, h is actually the y position at t equals 1/2. So it might help us to find t 1/2 first. And basically I'm calling it t 1/2 because it looks like it's halfway through its trajectory at that point. You'll find out that it exactly is exactly halfway. So I'm going to say t 1/2 is a y max. In other words, it's a maxima of y. So that's one way of thinking about it. That means I could say set dr over dt equal to 0 and solve for t. That's one way of doing it. Or we could think physically that what's going on here is I have an initial velocity vector v0 who has a x component v0 cosine theta and has a y component v0 sine theta. But each second that passes, v0 sine theta is going to decrease by 9.8 meters per second every second. So what you realize is the object reaches its max height when the when the y component of velocity is 0. So another way we could do it is we could say v sub y equals 0. Well, guess what? If I took the derivative of this thing right here and set it equal to 0, basically I'm setting this y part. I'm taking the derivative of that. That'll give me that part, and I'm setting that equal to 0. That's the same thing as me just setting the velocity in the y direction equal to 0. So I'm going to choose that. I'm going to say v0 v0 sine theta minus gt is equal to 0. Okay. Now, just for the record, let's go ahead and do this too. I am going to draw my x component of my velocity right here and my y component right here. Okay, so you can see that this is v0 cosine theta and this is v0 sine theta. Okay, that's why I got those. Okay, now if I solve this, I get t 1/2 is going to be equal to v0 sine theta over g.
I'm sorry, you probably already said this, but is G gravity?
Is what?
Is G gravity?
Yeah, g is gravitational acceleration, the 9.8 meters per second every second. Does everybody understand what I did there? So I've now got the time 1/2. Can anybody look at this and think about symmetry and tell me what you guess TL would be?
Two v0 sine theta over g.
Exactly. Yep. So that's just a guess. I would say hypothesis. TL is equal to 2v0 sine theta over g. And that was sort of what I was hinting at when I drew the t, when I called that first one t 1/2. So we'll see if that pans out. And I think you know it does. But anyways, now let's solve for h. Well, h is what happens. So h is y at t 1/2. Does that make sense to everyone? What I'm saying there? if I compute the y component of it at the time t1 half, then the y component, that is, of the r vector, right? Because at any point in time, for instance, right, this is r of t at any point in time. Okay, so if I set the y component of that to h and put in the t1 half, then I should get h. So what I'm going to do is I'm going to say h is equal to, actually, I keep changing colors of the pen and don't mean to. So I'm going to say h is equal to, if we remember what y was, it was v0 sine theta t. I got to put a 1/2 there now, minus 1/2 g t1 half squared. So that is actually what we had written down for the y component of the r vector. So now I just got to plug in that t1 half and that'll give me h. Well, I get v0 sine theta, and then t1 half is v0 sine theta over g. And then I got to subtract from that 1/2 g times. Now when I square it, I get v0 squared sine squared theta over g squared. Okay, you can see that one of these g's is going to cancel out with that guy. And that's going to give you v0 squared sine squared theta over g minus v0 squared sine squared theta over 2g. So I can make this a common denominator by multiplying by 2 in the top and bottom, and then I'll get h is equal to, this would be 2v minus 1v, so it's just going to be v0 squared sine squared theta over 2g. So that's our h. And you know that the sine function looks like this, by the way. But really the part that matters is just the first 90 degrees. So you can see, it wouldn't make any sense to have a theta greater than 90 degrees. Then you just draw the x-axis pointing to the left. But you can see that this is actually maximized at 90 degrees, which is like, duh, of course it's going to go highest if you throw it straight up. So we've got two of those things now. Now, what are we going to do for TL? Well, TL implies it's x at t sub L. That's one way of thinking about it, but that's not really what I want to do. Hold on. Let's say y equals 0 at TL. And x equals r at TL. So that should help us. What I can do is I can take my y expression, which I just used, by the way, and I'm going to say 0 is equal to, actually, keep flipping colors. I'm going to say 0 is equal to v0 sine theta TL minus 1/2 g TL squared. Okay. Now, in general, that might mean you have to use the quadratic formula, but in this case, we luck out because I don't have that other constant term. So this just becomes a simple factoring issue. I got 0 is equal to t times v0 sine theta minus 1/2 g t. So this corresponds to t equals 0. And actually, both of those should be written as TL. This corresponds to TL equals 0, which can't mean anything. That's when it took off. But this right here has to be set equal to 0 as well, and that will actually give me TL. So now I can see that TL is equal to, notice I'm going to put this on the other side of the equal sign. That'll become positive. It'll be 1/2 G. So I get V0 sine theta. That's this first term. And then I'm going to divide that by 1/2 G, which is the same thing as multiplying by 2 and dividing by G. So yes, your hypothesis was correct. It's twice as big as T1/2. So cha-ching. Now, if I put that in X, remember X is just V0 cosine theta times T, then I will get R. So R is going to equal V0 cosine theta times 2 sine theta over G, which equals V0 2 sine theta cosine theta over G. Thank you, baby. That right there is an identity. Does anybody recall the trig identity from that? This part right here is actually the sine of 2 theta. So flipping pages, I'm going to say R is in fact equal to V0 sine 2 theta over G. And that is a fundamental result. Now, some of these equations are labeled and numbered in your book. Some are not. I don't care. I'm going to allow you to use all of those equations that are boxed off on this one and this page, okay? Okay, so all the box equations can be used on your equation sheet. You got to know, though, of course, if I'm asking you, like, how far is it away is it going to land, and I'm shooting it from a cliff to some different level of land away, then you can't, it's not going to do you any good. You could still use it to figure out, for instance, the max height, but you'd have to say that's the max height relative to the height from which it was fired, and then you have to add the height of the cliff or something like that. But other than that, it's not all that useful. So if I give you a simple projectile problem that's launching and landing at the exact same height, then you're free to use all this you want, and I don't expect you to derive it. If I give you a different one, I'm expecting you to do the work on your own. Okay? Any questions about that?
I have a quick question about the landing time
Yes.
derivation. So how are you explaining canceling the V0 sine theta minus 1/2 GT landing, setting that equal to 0?
Okay, on this line right here, you mean?
Yes, yeah.
Okay.
Can we
Yeah,
go over
so-
that real quick?
Yeah, so it was basically V0 sine theta T minus 1/2 GT squared. That was Y from the R vector. Recall that?
Okay.
So this right here is what we used.
Mhm.
So I was saying when Y equals 0, that'll give us the time of the landing. So I just set
Oh,
that whole
gotcha.
thing equal to 0, and I factored out a T. And remember, when two things are multiplied and equal to 0, that means either one's 0 or they're both 0. And that's what I was looking at. So this one that came out in front, just a plain TL, if I set that factor equal to 0, I get TL equals 0. That doesn't make any sense. So we had to throw that out. But when I set this one equal to 0, I was able to get 2V0 sine theta over G.
I think you might be writing, but we can't see what you're writing.
Okay. All right. So,
Sorry.
yeah, I was sort of making marks trying to, but when I attacked this particular part, you see what I'm doing now?
Uh-huh.
Okay. When I set that equal to 0, I ended up getting this expression.
Right, so we're just using the other part of the expression then, only the x.
Okay, yeah, on this part right here, what I've done is went back and took my x, which was just this, and I plugged in TL for that t.
Okay.
So that's me plugging in TL right here. And you get 2 V0 sine theta. That's 2 sine theta. There's my V0, and there's my G. Does that make sense now?
Gotcha. It makes a little more sense. Thank you.
Yeah, good questions. All right, so the neat thing with this is, remember how I told you the graph of y equals sine x looks? Now, y equals the sine of 2 theta looks quite a bit different. In fact, if I call this pi and call this 2 pi, what's going to happen is it's going to go up like this and down like that. So all of that takes place by the first pi. This is pi over 2. And in fact, that peak is pi over 4. Right? So what that means is, one thing, if I want to maximize my range, theta max is equal to pi over 4, which equals 45 degrees. But if I do any other distance, notice I get 2 angles that work. You get a high trajectory and a low trajectory. Whoa, I don't know what happened there. So that's something we've learned about projectile motion knowledge. Now you can, if you're ignoring air resistance, you can go ahead and try to do try to throw it 45 degrees, and that'll get you your largest distance. So if you have to throw from the outfield to home plate in softball or baseball, then probably pretty close to 45 is a good decision to make. However, when you do include air resistance, sometimes you have to throw a little higher than 45 to make it go farther. And sometimes, depending on how the air is behaving, you have to throw it lower than 45 degrees. So the 45 is just a rule of thumb. And when we include air resistance, it doesn't quite work like that. But that said, it's now 7:50. I was going to do a problem where you imagine a monkey hanging from a tree of a height h, and you're going to shoot it with a tranquilizer dart so you can catch it and give it its shots. And the instant that the gun fires, that noise is going to scare the monkey, and the monkey's going to let go of the limb. So the monkey will fall to the ground. So should you lead the monkey by aiming below the monkey, or should you aim directly at the monkey, or should you aim above the monkey? Because you know that your bullet's going to be pulled by gravity. And it's, of course, your bullet's going quite a bit faster than the monkey, so do you shoot above it? In fact, you can work that problem on your own. They have a problem like it, where a kid's sitting on the side of a hill and shooting at a kid in a tree. It's essentially the same problem, but you can work it out with just in terms of h, the height from the ground to the monkey, and then L, the distance horizontally from where the monkey's hanging directly below him to where the bullet's leaving the barrel of the gun. And you can derive that, and that's what I was going to do. So that's the only problem I didn't get to finish, but that's okay. I might do it next time, or I might just do it on another video and put that online. So anybody have any questions? I'm going to wait here for the last person to leave. I was recording that last part. I may or may not be getting around to redoing the first part in video. I think I re-explained it pretty well, so that's probably okay. But anyways, I'm sorry for missing the whole almost first half of lecture with recording. So anyways, you guys are free to go, and I will see you again Monday. Have a great weekend. Don't forget to get your extra credit homeworks done if you want to, but also, or actually, I'm not even sure if they're mentioned marked as extra credit. The intro to MyLab and Mastering and the physics primer or primer, however you want to pronounce that. Those two are due on the 5th as well. And I'm going to try to change chapter 1 and 2 to do this past Tuesday, and that might help you a little bit. Okay.
I have a quick question. Oh, sorry, Gabby, you can go.
Okay, well, I just wanted to ask you, Professor, where can we access the previously recorded lectures again?
Okay, I'll type it up here. I'm going to send a message to everyone.
I wasn't sure just because I only saw like the older ones on Canvas, like from years ago, but I just want to know like where the recent ones were.
That's the website, youtube.com/Billy Younger Physics Solutions. That's my YouTube channel. And if you subscribe to it, which I do recommend you doing, and you can unsubscribe at the end of the semester. I'm not trying to make you forever my my follower, but if you did, that would help me anyways. But yeah, you can do that, and then every time I post one, if you get your notifications set properly, it will let you know every time I post something. But that's where I'm posting them.
All right, thank you.
No problem. You get to see a cool dog on there. If you do it, you'll see my little puppy.
That's a good incentive.
Exactly. Anybody else have any questions? Is Nora? Or
yes.
Okay, gotcha.
Yes, my question was about the practice test. I was wondering if there's a way you could enable the correct answers being shown. Oh no, wait. I guess not, because it's some of them might be on the test. That makes sense.
Exactly. Yeah. So
but,
I don't give that, but
hey.
Anytime you have one that's a bear, just take a photograph of it, a screenshot of it, and say, "Hey, Mr. Young, get it with the answers, not just it, but take a screenshot of the question with the answer choices." Maybe even the one where it's showing what you chose is wrong, and I will help you work that out. I can do it either by setting up a private meeting in Zoom, or I can solve it and do it in paper and send that to you or something like that, or I can do it in class.
Okay, sounds good. Thank you.
No problem. Brian, did you have anything?
Yes. So it kind of concerns the first part. So the very first part with
when I was doing the acceleration.
Oh yes, when you
I saw your notes in there. I saw where you had asked about how I got the -5 and stuff like that. Is that what you were looking for?
Oh yes. So for the first equation, for the acceleration equation with 1/2 times t squared plus initial velocity times time plus x0. So is x0 what was that again?
That's always just supposed to be the position that it had according to the x-axis at time t = 0.
Okay.
You can always set your origin there, so you can always make x0 0 if you wanted to.
I see. So after we plugged the x in the initial velocity and initial positions as 0, what we were left with was x = 1/2 times acceleration.
1/2 g t.
Sorry.
Yeah, you had like 1/2 gt squared. Or
yes.
After we factored out the t.
1/2 at squared. At squared. So after that, you set 30 meters equals 1/2 times 2 meters over meters per second times t squared. And then you said that t is equals to is equal to the square root of 2x over a.
Mhm. Which is a square root.
So I was kind of confused. Sorry, could you repeat that, please?
Yeah, I said, so the 2x over a became 2 times 30 divided by a, which was also 2 in magnitude, but it's in meters per second per second. So the 2 in the top canceled out with the 2 in the bottom, so you just left with the square root of 30. And the square root of 30 is about 5.48.
Can I try showing you what I have on my notebook? Because I think I may have missed a little bit of info.
Yeah, that's